folks, welcome to Lecture 1, which is titled Graphing One Variable. And this corresponds with Chapter 1 of the Minus the Math textbook. So to begin this lecture, we're going to first define some key concepts that are going to keep coming up and we're going to keep revisiting throughout the course. The first of which is an observation, which is one unit or an event, object, or person within a data set. And this is often represented as a row of data, right? So if you imagined a spreadsheet, the rows would be those that go from left to right on the spreadsheet. And then the other concept that we need to be aware of is a variable. And these are the characteristics of observations that can take on different values or amounts and are often represented as a column within a data set, right? So you could show this to yourself either through an Excel spreadsheet or the data viewer within Stata, right? You see the observations go from left to right, and each variable goes down the data set. Now, within the idea of a variable, we can make this distinction between a qualitative and a quantitative variable. So starting off with qualitative variables, these are also known as variables that are categorical or nominal, are variables that consist of categories that are not obviously ordered in any way. So I list a couple examples below here, one of which would be race, where in a data set we could code white as a value of 1, black as a value of 2, Latino as a value of 3, or other as a value of 4. Right, but there's no clear ordering in how we do that, right? It's not to suggest that one of these races is greater or less than the other. Same thing with industry, right? We could code manufacturing, agriculture, and technology as specific values, but it doesn't really mean anything, right? They're nominal, they exist independent of one another. Same thing with pregnancy. Not pregnant versus pregnant. A value of 0 for not pregnant versus a value of 1 for pregnant, right? There's no clear ordering there. They're just different states of being. Now, with quantitative variables, instead of having this ambiguous or sort of non-ordered characteristic, our values actually have a numerical ordering. So we can actually arrange these things from least to greatest, right? So age, if you're 5, that's less than 10. If your income is $100,000 a year, that's more than someone who makes $50,000 a year. Same thing with educational level, right? There's a clear distinction between a freshman, a sophomore, a junior, or a senior. Now, within this concept of a quantitative variable, there are 3 different types. So there's ordinal, discrete, and continuous. Starting first with an ordinal variable, that's a variable with values that can be clearly arranged from least to greatest. But it's important to acknowledge that the distances between these values cannot be easily quantified. Right? So going back to an educational example, right, we could have a variable that measures high school diploma or less, some college, 4-year college degree, and advanced degree. Right? Those clearly go from the least level of education to the greatest level of education, but we can't really quantify exactly what that distance is, right? A high school diploma or less, is that the same distance to some college as some college would be to a 4-year college degree, right? It's kind of messy, it's unclear. Now, discrete variables are variables that can only take on certain values within a range. So, in other words, they would take whole number values. And it's also not ordinal. And so an example of this would be number of children, right? You can't have 1.5 children. You either have 1 child, 2 children, 3, 4, etc. Same thing with the number of visits to the office, right? It isn't like you have a half of a visit. These are whole numbers. And then finally, we have continuous variables, which is a variable that can be measured to many decimal places, at least on a theoretical level, right? So weight, for instance, let's say you're a 200-pound male. You could raise it to a different level and say 200.0045 pounds, right? We can go to this very far level of precision that we wouldn't necessarily do in practice, but in theory we could do that. And that's essentially what qualifies this as a continuous variable as opposed to an ordinal. So now we're going to talk a little bit about the concept of percentiles. Right, and so the basic definition of a percentile is that the p% of the data falls at or below the pth percentile. And so if we replace those p's with an explicit example, we could say if the 25th percentile of age is 30, then 25% of the observations are younger than or equal to 30 years old. Or conversely, 75% of the observations must be older than or equal to 30. And so to find the pth percentile, we would need to line up all values from least to greatest and then pick the value that marks the p percentage point in this lineup. So for example, if we were trying to solve for the 50th percentile, we would pick the middle point. And importantly, there are various methods that can be used to deal with issues of ties and rounding, but we're not going to be focusing on those within this class. And so here's an example using real data of what percentiles look like, right? So we can see the change in income from 1967 to 2014 at the 95th, 90th, 50th, and 10th percentiles. And to get a little bit more into the topic of graphing within statistics, we're going to talk first about histograms, which are a specific type of bar chart that we use. And each bar within a histogram represents either one, a single value for a qualitative, ordinal, or discrete variable, or two, a range of values known as a bin, which condenses them, and that's for continuous variables. And so the height of each bar represents how many data points are one, equal to the corresponding value, or two, fall within the corresponding range of values, which would be the bin. All right, so here's an example of a histogram with a discrete variable, right? So on the y-axis, we have the frequency of which the number of times the teenager is reminded of something, right? So this is for 0 times, 1 time, 2, 3, 4, and 5 times. And what we see here is that the x-axis, which is the number of times the teenager is reminded, is then mapped onto the number of times that occurs in the data on the y-axis. And so here's an example with a continuous variable, right? And so a tip in theory is continuous, but within the data set, this is limited as just 1, 2, 3, 4. Right within here, there could be $4.25, $4.60, so on and so forth. But for simplicity's sake, we're just reporting this bin as the whole dollar. And so here's another example with, instead of the bin being at $1, it's now at 10 cents. Right? We can see how this pretty drastically changes the distribution of the data set, right? So we see that there's nearly 40 plus counts of $2 tips. And we see, interestingly, that most of that is at $2. People aren't tipping, $1.90 or $2.10, for instance. So something to keep in mind with when we're representing data graphically. Manipulating these axes can actually have profound implications for how we understand the data. And so another useful tool that we have in our toolbox are box plots. And these are especially useful for making comparisons. And so one of the examples we have listed here is, do sleep patterns differ depending on the day of the week? And in a box plot, the middle line represents the 50th percentile, also known as the median, and then the edges of the box are the 25th and 75th percentiles. And whiskers usually indicate the range, which would be the maximum and minimum value. And although outliers might be ignored within this data set, or excuse me, within this plot, those outliers will be shown as dots in particular. Right, and so what this has is the distribution on the hours of time slept in a night across each day of the week. Right, and so perhaps unsurprisingly, we see here on Friday and Saturday night, folks are getting a whole lot of sleep compared to, on like Thursday or Wednesday, right? So the median sleep time on Friday, Saturday, and Sunday is higher than the median on Monday, Tuesday, Wednesday, and Thursday, right? And on Friday, this sort of makes sense, right? We have some extreme outliers here who got hardly any sleep on Friday night, right? So we can think of some of the crazy partiers we may know. They're described in the data down here. But it's interesting once we put this graphically that we see such huge ranges here, right? And this makes sense. There are a lot of people that like to get caught up on sleep on a Friday night, but there's also some people that really just like to party and get no sleep. And so this final slide of the presentation is going to go over some graphing pitfalls, or at least some suggestions for how you can be more honest with the graphs that you're creating. And so in general, simpler is usually better. If you make a 3D graph or some of these other fancier graphs, they can be deceptive and misleading. Now, in terms of histograms, you need to be aware that the graph might look different depending on how the bins are drawn. Right, so manipulating the bin widths and starting points can make the distribution look different. And we saw that actually a couple slides ago. And then finally, as a note about the axes, you should always pay attention to how the X and Y axes have been drawn. And in general, any variation or change can be made to look very small or very big, depending on how the axes are chosen. And so there's an example here below that actually illustrates this point really well. Right, so this is the effective federal tax rate for the wealthiest 1% of households. Right, let's pay attention here at the x-axis and the y-axis. Right, judging by this graph, it looks like we see a pretty significant effect over time, that those tax rates have actually had a pretty significant decline. But what we actually see, right, when we look at this y-axis, is this is only maybe 4 or 5% throughout the range of this data. Now let's see what happens when we change the axis from 0% to 100%. Look how stable that actually looks over